From the previous classes, we have already gained some concept about types of crystalline solids and also about amorphous solids. Now let us go into details about crystalline solids. Okay, so first we will discuss about crystalline, crystal lattice and unit cell. So we have already know that in a crystalline solid, the constituent particles arrange in a ordered way, and there are a regular and repeating 3D patterns of constituent particles, and the regular 3D arrangement of the constituent particles in space is actually known as crystal lattice. Okay, let us now discuss about the characteristics of crystalline lattice. Okay, so at first the constituent particles are represented using points, and these points are known as lattice point or lattice site. Second characteristic is already known to us. According to these characteristics, each lattice points in a crystal lattice represents one constituent particles, which may be atoms, molecules, that is group of atoms, or an ion. Third characteristic is very important as it gives the definition of unit cell. So according to these characteristics, the lattice points are joined by straight lines to result the geometry of the lattice, and in the geometry of the lattice there will be a smallest repeating unit which actually repeating in different directions to give the entire lattice, or we can say that the entire crystal. Now coming to the definition of unit cell, the smallest repeating unit in the 3 dimensions which is composed of constituent particles and exhibit a definite shapes is known as unit cell. A unit cell can be characterized by its parameters. The first parameter is the length of the 3 edges A, B and C. These edges may be or may not be perpendicular to each other. Second parameter is the angle between the edges, which are as shown in the figure 1.6, in which angle alpha represents the angle between B and C, angle beta represents the angle between A and C, and angle gamma represents the angle between A and B. Total 7 combinations of the parameters are possible, which result 7 unit cells, and these unit cells are actually known as 7 crystal systems. Some basic descriptions of these 7 crystal systems are shown in the given table. The first column represent the crystal systems, different crystal systems, and the second column represent the subcategories of the crystal systems, and third and fourth column represent the the parameters. Okay, here the third column represent the edges, and the fourth column represent the angles, and the final the last column represents some examples, okay, of those crystal systems. The French mathematician as well as crystallographer Auguste Bravais in 1848 described using geometrical considerations that on the basis of arrangement of the constituent particles, total 14 different combinations are possible, and these combinations result total 40 different crystal unit cells, and these unit cells are known as Bravais lattice. Okay, so let us now find out how many Bravais lattice can be obtained or exhibited by the 7 crystal systems. We have already able to know that the 7 crystal systems are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral or trigonal, monoclinic and triclinic. The schematic diagrams of the different the 7 crystal systems is shown in the figure given in the presentations. Now let us discuss systematically about the 7 crystal systems one by one and their possible Bravais lattices. For cubic unit cell, we have already known that all the edges are equal for these unit cells. That means we can write A is equal to B is equal to C, and also the angles, the alpha is equal to beta is equal to gamma is equal to actually 90 degree for this unit cell. Total three kinds of Bravais lattices are observed depending upon the shapes of the unit cells, and these are number one is actually the simple or primitive unit cell, in which only the corners of the unit cell is occupied by the constituent particles, as shown in the given figure A. The second Bravais lattice for cubic unit cell is the face-centered cubic lattice, in which the corners of the unit cell is occupied by constituent particles. Additionally, at the center of each of the six faces of actually has one constituent particle, that is total six additional constituent particles is present in such Bravais lattice of cubic unit cells, as shown in figure B. The last Bravais lattice of cubic unit cell is body-centered cubic lattice, in which the corners of the unit cell is occupied by total 8 constituent particles, and additionally in the center of the unit cell one constituent particle is present, as shown in the figure C. Okay. Second Bravais lattice is tetragonal unit cell, in which A is equal to B, but B does not equal to C. Okay. So A is equal to B, and B does not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. Okay. The tetragonal unit cell shows two types of Bravais lattices. First one is primitive tetragonal unit cell, in which only corners are occupied by constituent particles, and the second is the body-centered tetragonal unit cell, in which additional one constituent particle is present in the body center of the unit cell. Okay. So coming to the third unit cell, that is orthorhombic lattice, in which actually A does not equal to B does not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. They will show total four types of Bravais lattices, which are primitive, end-centered, body-centered, and face-centered. All except the end-centered was not discussed. So in case of end-centered, two opposite faces of the unit cell are occupied by two additional constituent particles in the center of the two faces. The rest three are same as discussed above. Okay. The fourth one is actually the hexagonal, which exhibit only one Bravais lattice, which is primitive, that is only the corners of the unit cell is occupied by the constituent particles, and for this unit cell actually the A is equal to B, but it is not equal to C, and alpha is equal to beta is equal to 90 degree, but gamma is equal to 120 degree. Okay. So fifth 120 degree. So fifth one is rhombohedral or trigonal, which also only gives primitive Bravais lattice, and for these unit cells A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, but these are not equal to 90 degree. Okay. So this actually the sixth is the monoclinic, and it can gives two monoclinic Bravais lattices, which are primitive and end-centered, as shown in the figure. Okay. In this unit cell actually A does not equal to B does not equal to actually C. Okay. And alpha is equal to gamma is equal to actually 90 degree, but beta is equal to, in this case actually does not equal to 90 degree. Okay, it is different. Okay. And the last one is the triclinic unit cell, which only exhibit primitive Bravais lattices. Okay, in which actually A does not equal to B, does not equal to C, and alpha does not equal to beta, does not equal to gamma, or does not equal to 90. That means the alpha, beta, and gamma value are not equal to 90 degree. Okay. So in the above discussion we have encountered sometimes like primitive, body centered, face centered, in many times. Okay, so in the next class we're going to discuss about the number of atoms present in such unit cells. Okay.